integrated circuits, specifically the VLSI or ULSI circuits, you have to further translate the interconnection of components into a geometric definition defining how the different components are connected on a chip. Let me just show you by means of a small figure. So let us consider a MOSFET like this, which consists of this drain, gate, source and bulk. So suppose we want to define this MOSFET on a silicon wafer, or implement this MOSFET on a silicon wafer, then if this be the wafer, then I would demarcate an area like this, where this is the active region of the device, this is basically the polysilicon of the gate, and these two are the contacts where I will take the source and the drain. The substrate refers to the bulk. So all these terminals are depicted. So then in case of an integrated circuit, we have to go one step down from this to this, and fortunately enough, people have designed CAD tools to cater to all these requirements. So looking at the design loop for digital hardware, we start with our abstract knowledge about the system itself, and then we gradually translate it into a interconnection of components. And while we design our circuit, apart from our basic knowledge of mathematics to translate our logic equations into interconnection of components, we also use our basic design instinct to find out the possible areas of optimization in the circuit. And in fact, however intelligent your CAD tool can be, it will not be a replacement of the human intelligence, and that's why we end up saying that these tools are tools only, the actual designers are the human beings. The tools will only help you in speeding up the analysis process, but the tools themselves are not the designers of the circuit. You have to design the circuit, you have to use your intelligence to translate a description of behavior of the circuit into some interconnection of the components. So if you see the entire development process for an integrated circuit, once you design the circuit and simulate it and found that the results are okay, you further go for implementing a prototype of it. The prototype of it can take various forms. It can be implemented on some generic chip like FPGA or CPLD, to see that given the correct inputs, you can get the correct outputs from a chip, whether the timing requirements are met or not, and or you can fully implement the circuit using some integrated circuit chip, that means an IC, which we call an ASIC or application specific integrated circuit, to see whether the desired behavior from the circuits are met.
All the masks are based on only one chip for prototyping. All
Yeah. Yeah, so that depends upon the complexity of the chip. If the chip is simple enough, you can build a prototype of it, test it, and then go for further optimization. On the other hand, if the chip is complex enough, comprising of millions and millions of transistors, in that case, of course, you have to first implement it on some generic architectures and then test its behavior, see whether your requirements are met or not, and finally implement the circuit. So we understand that with the complexity of our design, our task of verifying whether the circuit is behaving correctly or according to our requirements or not is also becoming more and more complex. So while we use our intelligence and instinct to design a circuit, we are relying more and more on CAD tools for verifying the behavior of the circuit. So just like the human evolution process, the technology has also evolved over the years, and this is a nice picture in which the evolution of human being is compared with the evolution of mobile phones which we all use. So 10 or 12 years back, the mobile phones were like the cordless phones we use at home. They were giant in structures, and perhaps one in every 1,000 persons would have bought one such mobile phone. And I remembered in the late 90s, the call charges were as high as the outgoing calls used to cost around 14 or 15 rupees, and the incoming calls used to cost as high as 7 or 8 rupees. Today, even in certain certain providers are providing certain outgoing calls freely also, and we don't even think of paying for incoming calls unless it is roaming. So technology has evolved over the years, and thanks to the brain and intelligence of mankind, who is actually supporting this transformation on and on. So starting from these bulky handsets, it has become like the sleek handsets, and even nowadays you don't find keypads also. So in this mobile phone, you can see it is just touch screen based. So this screen itself contains sensors that will sense your finger and then provide the input to the processor. So if you expand your idea to the evolution of electronics, then if you go way back to 1896, when Thomson first invented electron, that was basically the beginning of electronics. So you can now imagine what radical transformation has taken place over the years. Today, by electronics, people mean programming some processor or programming some FPGA or something like that. And if you go just 20 years behind, by electronics, people used to still mean some vacuum tubes also. Not 20 years, I should say 30 years, because 30 years back it was 1980. So at that time people used to use vacuum tubes computers also. I have not used those vacuum tube computers, but I have seen them with my own eyes, how they used to look like. And So it actually reminds me of one thing my prof used to say, that when he used to do his PhD, that was in the early 70s, he used to do it in the Institute of Radiophysics and Electronics, Calcutta University. That was one of the reputed electronics institute until the mid 90s. And at that time there was a big computer built up of vacuum tubes that was there in one complete floor of IRPEL, that is Institute of Radiophysics and Electronics. And there were 7 or 8 operators who used to operate that computer, and people used to write Fortran programs to draw certain graphs, and when they used to hand over the Fortran programs which were punched on some punched cards and handed over to the operators, they used to say that, sir, please come after 3 days. By 3 days I expect to give you the results. So for a simple program which can be like plotting a sine curve or a cosine curve or something like that, they used to take 3 days, which people will simply laugh at if I tell them today. So that is how the things have evolved over the years. So starting from the motion of an electron between 2 electrodes in a vacuum tube, it has seen a radical change through the development of vacuum tube diodes, vacuum tube triodes, then semiconductor diodes, semiconductor transistors. And in fact, when people developed transistors, they thought that why not put multiple transistors on a chip. And in fact, Robert Noyce was first successful in putting 2 transistors on the same chip in 1958. That was the starting point of the development of integrated circuits, and therefore thereafter Gordon Moore and some others tried to refine on it and develop the integrated circuits. Gradually these integrated circuits evolved into microprocessors, and then people found out that with microprocessors things are too general enough and that may kill some of the time of, we may find out ways by which we can minimize the time of computation. So people started thinking of using vectored signal processing or seamed array processors and so on. And particularly for computational intensive applications, you need to, where you are finding that you are doing the same computation over a large volume of data, you can save the time of computation if you can compute on all the data sets on which you are computing in a similar fashion. And thereby came the notion of digital signal processors. People were still not satisfied with the performance, so they thought of using some generic chips like FPGA or CPLD for these computational operations. Even for very high performance applications where you are very much critical about the time within which you need to produce your results, you don't bother about the cost, you go for an ASIC of it. So that is how the chip design and the electronic circuit has seen so much transformation over the years. So why we are here to pull our hairs with all this stuff? The first thing is that, as I said, that the circuits that we are now designing are too complex, and in few years the complexity will be so high as to we can compare it with that of a human being also. But while the technology has seen a radical change over the years, the capabilities of human brain remains the same. So we have to find out approaches by which we can systematize our knowledge about the circuits and find out approaches by which we can rapidly analyze the circuits and produce some results. So we are in a situation in which we know that we have to develop certain software to analyze the circuits, and on the other hand we don't know how to develop it. So we go by the way in which a normal human being gathers knowledge. What is the process by which we gather knowledge? When a child is born, the entire world, including his parents, is unknown to him. Gradually he becomes aware of his parents, his surroundings, his family members, his house, his home, his environment, and so on. And so based on our existing knowledge set, we also borrow something from a peer knowledge set, add to it, and develop our knowledge set. That is the basic philosophy by which we keep on expanding our knowledge. And we try to apply this philosophy for developing the notion about circuit analyzing softwares. So the existing notion is that we know that the software engineers go by a certain philosophy by which they develop softwares, and we try to use that philosophy for analyzing the behavior of circuits. So when a software developer develops a software, what do they do? Suppose you give a software development problem to your students. What will they immediately do? If it is a group of 4, they will first split up the entire problem into 4 modules, that they distribute the individual modules amongst themselves and start developing the individual modules. Further, they in each module given to each student, they will find out the submodules of which they will go on splitting the modules into submodules, sub-submodules, and so on, ultimately arriving at the elementary level modules, which are of manageable sizes, so that they can develop those modules. And once the elementary level modules are developed, they can be integrated into the whole system. So that is what we really mean by this hierarchical design, in which we split a system into its subsystems, and again the subsystems are split into its sub-subsystems, and so on, ultimately arriving at the elementary level modules, which you can develop and integrate it into a design for the whole. The other problem which you may not understand that much in today's scenario, because today the entire world is basically a graphical world, so you may not perceive the problem too much, but it was there even 10 years back also. So that is the interface through which you are communicating your ideas to the computing system is a text based interface. Even when we were the BTech students, we used to write our ideas about the circuit in some editor, like the editor in which you write your C program, and then compile that program and get the output about depicting the behavior of the circuit. So that was the notion used by Jonathan Nagel and its associates at the UC Berkeley when they developed the SPICE, because while Nagel was working on circuits, Nagel started to work for his PhD on some circuit design and analysis procedures, and then it occurred to him that when mechanical structures, building structures, they are analyzed by means of programs, why not electrical and electronic circuits are analyzed by means of these programs? And out of this thought evolved the notion of SPICE, which we use even today. Today we may be using graphical user interfaces for designing circuits, then some nice looking programs for analyzing the circuits, but at the basic level we are using the same SPICE which was developed by Nagel and his associates. However, there is a strong but to all these things. In case of a software, we go by a traditional fetch, decode, execute model, which means we sequentially go on fetching instructions on the memory, decode them and execute them and produce results. On the other hand, when we are required to model the behavior of hardware, if two modules exist in a system and are given the same set of inputs,